In this lecture, we will introduce how to use a thermistor to measure temperature. As you've seen in the previous lecture, there are different ways to measure a temperature. This week, we're going to be using a thermistor, and that thermistor will be very similar to the one that you used in a previous course. And what you will do is use that thermistor in a series circuit, a voltage divider circuit, and from that circuit you will be able to perform an analog to digital conversion and determine what the temperature is and then display that on the LCD. You're going to have to do repeated analog to digital conversions, so you're going to be reading the analog value coming off of this circuit and then updating the display so that as the temperature may change around the thermistor, you are updating the display with the current temperature value. So in the previous lab, you performed an analog to digital conversion of a signal coming off of a potentiometer. And then you use the 7-segment displays. In this lab, we're going to still perform an analog to digital conversion, and you will still display the value coming off of the analog to digital conversion, but instead of using the 7-segment displays, you will now put that on the LCD. And also you will want to make sure that your potentiometer switches are turned off, because we're not going to use those in this upcoming lab. So if you remember what you learned about thermistors in the previous lecture or from your circuit analysis class, they have this exponential form they take on here. So you've got a nominal resistance, R0 or R0, that exists at a nominal temperature, T0 or T0, and depending upon what the temperature T is, the resistance of that thermistor can either go up or down. And so the rate at which it changes with respect to temperature is determined by this beta value. And depending upon whether you have a resistor that will be going up in resistance as the temperature goes up, or one that will be going down in resistance, that determines whether you have a positive temperature coefficient or a negative temperature coefficient. In this particular case, your resistance will be going down as the temperature goes up. In this lab, we will be using a thermistor that has a nominal resistance of 10 kiloohms, and the nominal temperature is 298 Kelvin. Recall that the temperatures in this formula are entered in Kelvin, so you will have to convert from Kelvin to Fahrenheit or Celsius if you want to use another scale. In the circuit analysis class, the beta value for those thermistors was 3903.7. The ones that you're going to be using in this lab have a nominal beta value of 3950. The way we are going to build this thermistor circuit is to create a voltage divider. That voltage divider, as you remember from circuit analysis class, has two resistors, and it basically creates a proportion of an overall voltage as an output voltage. And so you will use one fixed resistor, and then you will use the thermistor in a voltage divider circuit. And depending upon what the output voltage is, that will tell you what the current resistance is, and from that current resistance you know what the temperature is as you work backwards. It's a good idea when you're making such a voltage divider circuit to choose a known resistor that is similar to or equivalent to the nominal resistance of your thermistor, and we will do just that. In this lab, we will use a nominal 10 kiloohm resistor as our known resistance, and we will also have a 10 kiloohm thermistor in the circuit. So let's remember our old friend the voltage divider from circuit analysis class. And the way these voltage dividers work is you have an input voltage, and then you create this proportion here such that some of the voltage is down here at V out, and then the rest is across R1. R1 here is going to be our known fixed resistor, and then R2 down here is going to be our thermistor. And for this circuit, we're going to let V in be 5 volts. We can easily source that off of our trainer kits. And we are going to let R2 be our thermistor here, and R1 is going to be a 10K known resistance. And we have some math down here that will help us to understand how these circuits work. So basically taking this and dividing through both sides by Vn, we see that we can get this proportion over here on the right hand side. So we can express the ratios of the output voltage to the input voltage the same way as the ratio of the resistances as you see here. You can also think about that as being the same ratio as the analog to digital conversion. So if you were to do an analog to digital conversion of the input voltage, that would be the maximum A to D value that you could get, because our input voltage is going to be the same as our voltage boundary for the analog to digital conversion. And if you were to take the result that you get out of the analog to digital conversion divided by the maximum, that proportion is going to be the same as the output voltage divided by the input voltage. So from that, you can figure out what your resistances are, and for the resistance for the thermistor, because you will know the known value, you know what the maximum is. In this case, we have a 10-bit analog to digital converter, so the maximum value is going to be 1023. And then your A to D result is what you will have the microcontroller compute for you. So we can go through a little bit more of the math here. We're going to put in a wire just to measure the voltage at the node that is between our two resistors, do the digitization of that, and then in order to get the A to D result, this is our formula here. And then our maximum A to D result is that, and we will solve this for our thermistor. Our thermistor at this point is the only unknown in this equation. And so once we have the thermistor resistance, then we can go back and plug in this equation. We know what R naught is. That's going to be our 10 kiloohms. We know what our T naught is. That is 298 Kelvin. And then we know what our beta value is. That is the 3950. And so E is the natural number here. We can actually just solve and get back our T value. And so remember, T is going to be in kelvins, and you can convert that back to Fahrenheit. And here are some of the formulas that you can use to do that. If you have a temperature in Kelvin and you want to convert it to Celsius, you simply add 273.15. If you have a temperature in Celsius and you want to convert it to Fahrenheit, this is the formula that you will use. You will note that within your processing of the temperature and the thermistor resistance, you will need to remove that E, and to do that you will use a natural log or ln function. You can do that within C, which is what we will use in this lab, using the function log with a paren and then the number of whatever you need to take the log of. That is not naturally built into C unless you include the math library. So if you put an include math.h, that will allow you to do logarithms. I want to spend a few moments talking about how division works in C. So in C, if you take two integers and you divide them, they simply truncate and throw out any remainder that might exist. Sometimes that's good for us, sometimes that's bad. So if you're trying to isolate a specific digit to display on a 7-segment display or an LCD, you might want to isolate that digit and get rid of the remainder and just display the digit you're interested in. Sometimes you want to maintain a fractional portion, and so in that case you can do that one of two ways. You can either declare the variable that will hold that as type double, or you can have something that does have an integer and then cast the result to a double after some integer division. So let me give you an example of that. So here, if you had an integer value called int value, and you wanted to do some computation that would be double-based computation, something that will have a fractional remainder, you can put parentheses, double parentheses, that does typecasting of this integer value into a double, so that for all practical intents and purposes, that integer is treated like a double, and therefore if you do any division, multiplication, addition, all those types of things, it will maintain the fractional portion. You can also go the other way. So if you have a double and you want to convert it to the nearest integer, then you can just do int my double, and that will cast the double value into an integer so that you can do processing that particular way. So in some cases you would want to keep the fractional portion, in other cases you may not. When you're talking about computing resistances and temperatures and all those types of things, you may want to keep them as doubles until you get to the final values that you are going to be putting out onto the display. So here's how casting can work in arithmetic. If you had a variable called myvar and you divided it by 5, that will give you an integer value. It will not keep the fractional portion. But if you divide by 5.0, effectively the same thing, this is a double, and assuming myvar is a double, or you've cast myvar into being double precision, this will give out a double. It's very subtle, but it is important that you know the difference between integer division and double division. So in the lab assignment, you're going to want to use casting most likely everywhere until you get to the final temperature to put out to the LCD. And you will want to keep 1 decimal place of accuracy for the temperature. So I highly recommend you maintain all of the decimal places and then simply get rid of that at the end. You can multiply by 10 before you cast it to an integer so that you can preserve the 10th place in your value that you compute for the temperature. You can use an array to look up values, but remember the indices for arrays have to be integers. It doesn't make sense to say give me array element 2.5. That does not exist. So in that case, if you are looking up values, you will need to cast them to an integer. And that's very important that you do that before you look up, say, ASCII values to go on to the display. So in terms of displaying, you're going to do this very similarly as you did before, just to isolate the individual digits, but your lookup values will be different because instead of turning on the 7-segment displays, you're going to be using the LCD. So in this case, what are you going to put on the LCD in the lab? The top line, you're just going to put the analog to digital conversion results. So that'll be a 4-digit value between 0 and 1023. And then the second line, I would like you to, in the lab, display the temperature in Fahrenheit. And we will just do room temperature. We might also put it into hot water or into some ice so you can check different ranges of temperatures that you can measure. The sampling speed is going to be configured in 80con 0. And we don't really need the fastest sampling speed possible because we know that the temperature is not going to change very rapidly, so you can sample a little bit slower and that will be fine. So let's just go over the order of operations. When you first get in to the code, you're going to have to do all of your port configuration, so you're going to properly configure your tris registers, make sure whichever analog channel you're using does not conflict with your use of the LCD pins, and also is set as an input. And then you will need to correspondingly set the bit in ANCEL or ANCEL H to make that an input while clearing the bits that need to be digital outputs. And go ahead and configure your 80con 1, which will determine whether you are right or left justified on your results, and will also determine your the range of values. So in this case, you would want to establish your boundary as 0 and 5 volts. And then configure your 80con 0. So that will tell you which channel you're going to be using and those types of things, and your sampling rate. And then tell the A to D to go on the next cycle. Wait for the A to D to finish. You can do an interrupt service routine, or you can poll the go bit, whichever one you choose. And then after it is finished, you will want to compute the analog to digital result. Remember, that's going to be spread across 2 registers. You're going to need to multiply and add together. And then go ahead and display that result on the top line. That's a good first cut. If you can get your circuit built and do that, and then start seeing the A to D values change, that's a good first step. Then what you'll want to do is work back with the math on the A to D result to get back to a temperature. And you're going to get some practice this week for your in-class assignment in figuring out the mathematics you need to do that. Then on the second line, you're going to display the temperature to 1 decimal place of precision on your LCD, and you'll just display that 1 character at a time. Don't forget your decimal place, and then you can also put in the degrees and the F.